Hello everyone. So now let's just do another example here. Okay, so first I want to look at the limit as x approaches infinity of my numerator, my ln x function squared. And so what I'm going to do first is just look at the end behavior of my function ln of x. And so what do I mean by that? Well, as x gets bigger, what's happening to my function values? What's happening to those outputs? Alright, so as x goes to infinity, or in other words, as x gets bigger, you also see that your output values or your y values are getting bigger, right? And so that means then that the limit as x goes to infinity of my function ln x is just infinity. Alright, and so that basically again just means that as my x values are getting bigger, so are my y values. And so that's why I'm saying the limit as x approaches infinity of the natural log of x is equal to infinity. Okay. All right, and so basically, I'm just saying that going back to the limit as x approaches infinity of my numerator here, I'm basically saying that this is just infinity squared, which is infinity, all right, because I know that the limit as x approaches infinity of ln of x equals infinity. It's the same idea here with the ln of x squared. It just becomes infinity squared, which is just infinity. Okay, and so you could also, if you wanted to, put ln of x squared, like that function, into Desmos and convince yourself graphically that that's the case, that as your x values get bigger, so do your y values. But anyway, this is how I do it, like algebraically speaking. Okay, so now looking at the bottom here, and now I want to look at the limit as x approaches infinity of the denominator. And so we remember, hopefully, that x squared, that's just an upwards U shape. And so what's happening as my x values are getting bigger, so as my x values are getting bigger, so are my output values or my y values, right? And so I would say then that you would say as x goes to infinity, f of x goes to infinity, or it approaches infinity. And so in terms of a limit, that just means the limit as x approaches infinity of x squared is also infinity. Okay, and so since I have that the limit of the numerator is equal to infinity and the limit of the denominator is equal to infinity, I'm in this indeterminate form of infinity over infinity. And so we can use L'Hopital to come to this conclusion. So then, by L'Hopital's rule, we have the limit as x approaches infinity of this is equal to the limit as x approaches infinity of the numerator, derivative of the numerator divided by the derivative of the denominator. And so this just gives us the derivative of parentheses to a power is bring down the power, copy the parentheses to the power minus 1, which would be 1, times the derivative of the parentheses. And then this is over 2x. Okay, so simplifying this now algebraically, this is the limit as x approaches infinity of 2 ln x over x over 2x. I don't even know what was happening there, sorry about that. Okay, and so this is equal to the limit as x approaches infinity of 2 ln x over 2x squared. And so this is just equal to the limit as x approaches infinity of ln x over x squared. Okay. So now at this stage, we actually already learned a limit technique that would tell you that this limit is 0. And so if you remember, it's because we had our exponential growth functions, or, our functions with a base that was bigger than 1 to the x, right? So our exponential functions, we said that those go to infinity faster than our power functions, which was just our x variable to a number, which goes faster than our natural log function. Okay, so basically what I'm saying is the natural log was the function that was going slowest to infinity, whereas x squared would go faster to infinity than the natural log. And so we said that limit was 0. All right. And so we know that from unit 1, going back to those notes, you'll see what I'm talking about, that this limit is equal to 0. Okay. But we're going to show that using L'Hopital's rule by just applying it again. Okay, because if you notice, the limit as x approaches infinity of the numerator is infinity, and the limit as x approaches infinity of the denominator is infinity. And so I can now use L'Hopital's rule to figure out this limit. So since okay, so basically rewriting everything how College Board wants us to, right, where we say, okay, well, the limit of the numerator is equal to infinity and the limit of the denominator is equal to infinity. So then by L'Hopital's rule, I can say that that limit is equal to the limit of the derivative of the top divided by the derivative of the bottom. And so I get that this limit is going to be 1 over x divided by 2x. And so when I simplify this, I get that this is 1 over 2x squared, and so this limit is 0. Okay, because we run into that 1 over infinity case. And remember, we said 1 over infinity within the limit went to 0.